QA, where you will get to ask questions to any of the authors. So for the first paper of the session, we have the paper Achieving Diversity in Counterfactual Explanations, a review and discussion, and this will be presented by Adulam Jayasothi. And welcome, Adulam. You can just click on the PowerPoint and open your slides.
So, hello everyone. I am Adulam Jayasothi. I am a PhD student in Sorbonne University in Paris. I present you today our paper, Achieving Diversity in Counterfactual Explanations, a review and discussion. This paper was written with Thibault Logel, who is just here, Marie-Jeanne Lesaut, Christophe Marsala, and Marcin Detinic. So in this paper, we present several contributions. The first contribution is a survey about different methods of the state of the art which generate diverse counterfactual explanations. We propose to characterize them according to different criteria, in particular the type of diversity they consider. Our second contribution is a discussion about the motivation of the needs of giving several explanations to the user. And we propose also a discussion on the difficulty of choosing an aggregation function to combine several criteria in case where we want to give just a single explanation to the user. So in this presentation, I will focus on the discussion part, and I invite you to read our survey in our paper. So there is a lot of different types of explanations in XAI domain, and we particularly interested in a counterfactual explanation. So first, what is counterfactual explanation? Is all the modifications the user has to do to have another prediction by the model F. So this type of explanation is defined as all the instance in another class, and more often, methods which generate this type of explanations are minimizing a cost function which represent the quality criterion of an explanation. So the final explanation is the difference between an instance in another class E and the studied instance X. So this difference represents the modifications the user has to do. So as I say, there is a lot of different methods in the state of the art that generate this type of explanations, and they present numerous definitions of the quality criteria. Some of them are only based on the studied instance and the final explanation. Others are considering some information about the data. And finally, some of them are integrating some knowledge about the user. So there is a lot of different ways to define the quality criterion of an explanation. So the big question is which quality criterion we have to choose to give the best explanation to the user. One solution proposed by many papers is to aggregate different criteria into one to generate just a single explanation. But it can be a problem, and I will explain you why. The combination of several criteria is not an easy task. It can be difficult for two reasons. The first reason is that the explanation that we give is rarely optimizing all the criteria that we consider. Because sometimes we consider criteria which can't be optimized in the same time, so the final explanation is not fulfill all the objectives that we consider. The second reason is that when we have several criteria, we have to choose an aggregation operator to combine these criteria. And this task is very difficult because it has an impact on the final explanation. For example, here we have the half-moon dataset, and for a particular instance represented in green, which is predicted here in the blue class, we generate several counterfactual explanations. Each explanation is associated to a different aggregation function, and we see here each explanation is in different zone of the feature space. So that shows how much the choice of the aggregation function has an impact on the final decision. And it's too risky to choose one explanation from them to give to the user because it can be not adapted. So one solution to this problem is to propose not one single explanation to the user, but several explanations. And this principle is also defended by different papers, in particular in teaching concept, where they say that giving several explanations to the user helps to increase the understanding of the explanation. And also, we want to give an explanation which is good in any cases. That means for different type of user, different context, and different needs. And giving one single explanation can't permit to satisfy all these constraints. So one solution is to give several explanations and let the user choose which one is the best for him. So the final explanation is not just one counterfactual example, but a set of counterfactual examples. And this set of examples has to be diverse because it will be not interesting to have the same information from each example. So the new question is how we can define the diversity between counterfactual examples. There is already a lot of methods which studies this question, and based on this method, we propose a typology of diversity where we define 3 families of diversity. Diversity in criteria, diversity in the feature space, and diversity in actions. So first, diversity in criteria aims to give some explanation which are associated to different criteria. So we can have this explanation by doing different trade-off between criteria or by optimizing each criterion independently. Diversity in the feature space aim at having counterfactual in different zones of the feature space. So we can have this counterfactual by adding a new diversity criterion in the feature space, in the optimization problem, or by solving several optimization problems on different subspaces. And finally, diversity in actions aims to propose explanations associated to different types of modification. So the modification can be done on different features or in different directions. So now we define 3 families of diversity. We propose a survey which groups 33 approaches of the literature. This approach proposes This approach proposes diverse counterfactual explanations, and we propose to compare them according to different axes. So here we have an extract of our survey. The first axe is the type of diversity that I just presented before. Then the diversity criterion, which is how the diversity is integrated in the algorithm, and 3 other criteria. So the number of counterfactual. So this is who choose which, how many counterfactual is generated. Then if the method is explicit or not. So that means if the diversity is explicit in the method or not. And finally, if we have to do several runs or just one single run to have the explanation. So to conclude, we see that the aggregation of numerous criteria to generate just a single explanation is not an easy task, is a very big task, because finally we can have an explanation which is not adapted. So one solution to this problem is to propose not a single explanation, but several explanations. And it's better if these explanations are diverse, because we want different information from each explanation. We propose a typology of diversity criteria. So this is by defining 3 families of diversity: diversity in criteria, in the feature space, and in actions. And finally, we present a survey on the generation of on the methods which generate diverse counterfactual explanations. So this survey can help people to choose the method which is more adapted in different cases. And for our future works, it will be interesting to do some experimental study, as any study in XAI domain, to know which type of diversity is preferred by the user, and also study diversity for other type of explanation beyond counterfactual explanations. Thank you very much for your attention.
Thank you very much, Adulam. And for the second talk, we will hear from the paper Saliency Cards, a framework to characterize and compare saliency methods, and this will be presented by Angie Bogust. Thank you very much, Adulam. And for the second talk, we will hear from the paper Saliency Cards, a framework to characterize and compare saliency methods.
Cool. Hi, everyone. I'm Angie Bogust, and this is Saliency Cards, transparency documentation to characterize and compare saliency methods. So saliency methods are powerful tools to explain machine learning model decisions. They tell us which features contributed the most to our model's output, and they can help us identify if our model is doing something reasonable or red flag when it isn't. But as research in this space has grown, so too have the number of saliency methods, and it can be hard to know when to choose one over another. So far, we've evaluated saliency methods under this notion of faithfulness, which says that a saliency method should accurately reflect the model's underlying decision-making process. And this is an admirable goal, but the saliency interpretation pipeline is quite broad. There are many different types of saliency algorithms that all have different outputs and are ultimately interpreted by a human differently. Under this notion of faithfulness, every saliency method needs to be sensitive to input changes, to changes in the model, be minimal, and so on and so forth. And it's unlikely that a single saliency method can achieve all these attributes of faithfulness. And more importantly, it's unlikely that every use case of saliency methods actually needs all of these attributes. So instead of this singular axis of faithfulness, we break it down into 10 user-centric attributes that span different parts of the saliency interpretation pipeline, including methodology, sensitivity, and perceptibility. Methodological attributes describe how the saliency is computed. For instance, hyperparameter dependence is a methodological attribute that measures how sensitive the saliency method is to user-specified parameters. Some saliency methods, like integrated gradients, rely heavily on their parameters, and depending on how we set, in this case, the baseline parameters, we can get drastically different saliency maps, which could be misleading. So it's important to know that we need to spend that additional time to properly set these hyperparameters, or if we don't have the time or expertise to do so, choose a method that has less hyperparameter dependence. Methodology also encompasses determinism, semantic directness, model agnosticism, and computational efficiency. Sensitivity attributes measure the relationships between the saliencies, the model, and the data. So for instance, model sensitivity measures if the saliency method is sensitive to meaningful changes to the model's parameters. Unlike the methodology attributes we just looked at, which are descriptive, the sensitivity attributes can be evaluated through categorizations of existing saliency method tests. One of these is randomization. So if we progressively randomize the model, the saliency method should also become progressively random. And model sensitivity has corollaries to the inputs and the labels. And finally, perceptibility attributes describe how humans interpret the saliency. So minimality measures how many unnecessary features are given importance. Some saliency methods, like vanilla gradients, are known to be noisy, while their smooth variants can look more sharp to people. This can be important if we have to manually look at a large number of saliency maps, or if we don't want noise to convey unwarranted certainty. And just like sensitivity, the perceptibility attributes are testable. So we can test minimality based on the subsets of features or even human evaluations. And perceptibility also contains perceptual correspondence. We then use these 10 attributes to structure saliency card documentation, which includes descriptions of the saliency method's methodological attributes, the results of sensitivity tests, and of perceptibility tests, which results in this concise and consistent documentation format that can reveal strengths and limitations of a saliency method and allow users to directly compare between them. We worked with users in their saliency tasks to see how saliency cards would work. We looked we spoke to saliency developers, machine learning researchers, and domain experts, including consultants, computational biologists, and radiologists. And all of these users use saliency methods on a quite diverse range of tasks. So while some users do the canonical saliency method approach, where we visually analyze a few saliency maps to understand our model's behavior, others would embed them into interactive interfaces, and some would actually never look at the saliency maps at all. They would just use them to compute quantitative aggregate statistics. And despite these very diverse settings and being familiar with a large number of saliency methods, users primarily chose methods based on popularity and ease of use, as opposed to methods that are most appropriate for their goals and tasks. Instead, with saliency cards, they were able to choose the attributes that were important to their goals and then use those to select a task-appropriate method. So for instance, that machine learning researcher who used saliency methods to compute aggregate statistics decided to prioritize computational efficiency, since they needed to run the saliency method on every instance in their data set, and didn't prioritize model agnosticism, because they were only ever going to work with convolutional models. Using these and the rest of their priorities, they were able to use saliency cards to find that GradCam would be an appropriate saliency method for them. However, people's goals often differed, and their prioritized attributes also often differed or even conflicted, even within the same role. So another machine learning researcher used saliency methods to analyze the fairness of classical machine learning models. They didn't care about computational efficiency because they work with small data sets, but they did care about model agnosticism to make fair comparisons across their different models. And the fact that users' priorities often conflicted sort of points to the fact that there may not be a single best saliency method for every use case, but instead some that are more suited to some tasks than others. Beyond selecting a task-appropriate method, saliency cards also provided us a vocabulary to discuss saliency methods. So currently, we often say that noisy saliency maps are hard to interpret, especially for non-experts. So if we're working with non-experts, we should prioritize minimality. However, we spoke to a radiologist who had little to no machine learning background, and despite this, they were able to use the user-centric attributes to understand what their options were for saliency methods and describe their priorities. We found that they're actually very accustomed to using noise in medical imaging to attenuate measurement uncertainty, so they really didn't care about minimality at all. And this vocabulary allowed them to describe what their priorities were, and potentially in a deployment setting, work with their computational counterparts to end up with a saliency method that really reflects their goals and their expectations. And finally, saliency cards can reveal areas for future development. So as we characterized different saliency methods, we found that some methods have been more thoroughly evaluated than others. So users wanted more tests, more evaluations, and a more diverse set of tests across different domains and models. We also found that using these attributes revealed gaps in the landscape. So for instance, oftentimes model agnosticism and computational efficiency are at odds with each other because we achieve model agnosticism through repeated perturbations. But some users wanted both of these attributes. So we could look at new saliency methods that can achieve both things, or theoretical principles that can tell us that maybe these two are always at odds. And finally, we hope that saliency cards are really living documents that change and evolve as saliency methods and explanations change and evolve. So, it could be that currently our attributes are maybe too broad and need to be narrowed, or as new users start to use saliency methods in different domains, that new priorities and thus attributes will come about. To that end, we have a centralized repository of saliency cards that contains saliency cards for existing methods as well as templates, and we would love for you to contribute to it. So if you have a new method you would like to include, you have new evaluations you'd like to report, or you'd just like to suggest new attributes or ways the framework could change, I'm happy to review pull requests and I'm happy to talk about it. So thank you.
Thank you very much, Angie. And next, we have the paper Robustness Implies Fairness in Causal Algorithmic Recourse. Do we have the author in the room? Okay. So I encourage you all to take a look at the paper, and we'll have some extra time at the end to ask questions, which I'm sure you're all excited about because we already have a lot of interesting things to discuss. So we will now go to the fourth paper in the session. And for the fourth paper, we are going to have the paper Personalized Pricing with Group Fairness Constraints. And these will be presented by Shezheng Zhu.
Good afternoon, everyone. I'm Zexing. I'm currently a fourth-year PhD student at University of Illinois at Urbana-Champaign. Today, I'm going to present our paper on personalized pricing with group fairness constraint. This is a joint work with my advisor, Professor Xing Chen from Georgia Tech, Professor Yuan Zhou from Tsinghua University, and Zi Shuo. In the big data era, due to the more availability of customer information, personalized pricing has become a very popular strategy which sets different prices for the same product according to individual features. However, there are some issues occurred in the personalized pricing due to the concerns over fairness which can be potentially caused by the price discriminations. So usually the protected groups have higher valuations over a specific product, and they will be charged higher prices, which cause the price disparity against those sensitive groups. Especially when the sensitive attributes are like race and gender, this gonna cause some illegal issues. So one popular phenomenon is called pink tax, which we can see in the figure below. We can see that females are usually charged higher prices for the beauty product and services. So to regulate this, so recent regulations have been made to ensure fairness in the business world, such as the treaties proposed by the Federal Trade Commissions. So to address these issues in this paper, we're gonna answer the following two questions. So the first is how to model the fairness in the context of personalized pricing, and what is the impact of the fairness constraint. So our work basically falls into the following three streams of literatures. The first is personalized pricing and price discrimination, which is the context of our work. And the second is the fairness in pricing. So previous works has been studied the non-contextual pricing setting, while our work focused on the contextual pricing setting. Moreover, we define the fairness regulations quite differently from the previous existing literatures. And our work also broadly related to the algorithmic fairness. So in the machine learning world, we all know that there are several fairness metrics proposed, such as the equalized odds or accuracy parity, while in our work, we adopt the statistical parity. But we also define it differently under the pricing context. So let me formally introduce our personalized pricing work. So we consider a scenario where a monopoly is selling a single product to multiple customers, and the seller has access to the customer's features, X tilde, and the X tilde contains two parts. The first part is the non-sensitive feature part, X. You can think of it as some customer purchase histories or their membership in a specific online platform. And the second, capital S, is their sensitive features, which you can think of that as their gender, their race, etc. And we assume that the feature vector X tilde follows some distribution known by the seller. And we also assume that each customer with the sensitive feature and all the other features x tilde follows has a value function v, which follows feature dependent distribution. And we also defined admissible price set P to be a bounded set, which can be either continuous or discrete. And we define our pricing policy to be the rho function, which maps from the feature set to the admissible price set. So the personalized pricing procedure works like the figure below, that when a customer comes, the seller observes the customer feature x tilde, and then based on that x tilde, the seller will offer a price. And then the demand will be realized according to the customer's valuation and the price set by the seller. So if the valuation is larger than the price, then the customer will buy the product. Otherwise, the customer will not buy the product. And finally, the goal of the seller is that they want to maximize their revenue and subject to the fairness constraint, which we will formally introduce later. So the goal of the seller is to find a pricing policy that not only maximize the revenue, but also concern of the fairness. So the goal is still the expected revenue, which we define to be the expectation over the product of the demand and the price. And to better understand our price constraint and to define the price constraint, we first introduced the group membership function G, which maps from the sensitive features to group labels. And in the fairness constraint, the QU is the probability density given by our pricing policy for group U, and the QU tilde is the probability density given by the pricing policy of the unconstrained problem. And the D here is the distance metric, which we consider the total variation distance and the earth mover distance in this work. And the fairness degree delta is to be ranging from 0 to 1. If it equals to 0, it means this is the perfect fairness. And if it equals to 0, it means we do not consider fairness at all. So let me formally introduce our fairness measure. So previous existing works, they already considered to measure the distance of the single price policy or the mean price policy. However, in our work, we go beyond the simple moment-based constraint. We consider the full distribution of the pricing policy. So here, by considering the full distribution, we can capture a wider range of fairness concerns. So to solve this problem, we reformulate our stochastic formulation as a linear programming problem by the sample average approximation. And in this algorithm, we consider a group of n customers, which is allocated to k groups. And in each group, we have NU number of customers. And we have L number of admissible prices. And the decision variable Fiju here means the probability of customer I being assigned to price J in group U. And the another decision variable alpha Ju means the proportion of the customer in the group J in the group U that have been assigned to price J. And moving on to the constraint, the first constraint tells the price distribution of customer I in group U, and the second constraint considers on the group level. It represents the probability of taking price J of group U. And to move on to the group fairness constraint, we restrict the discrepancy of the price distribution of two groups to be no further away by delta. To bridge a gap between the continuous price set and discrete price setting, we showed that there is an order of 1/L gap between the two settings. And under some mild conditions, we also show that this bound can be improved to 1/L squared. So let me show you some exciting experiment results. So in this study, we adopt the data from Jingdong.com, which is one of Chinese largest online retailer, like Chinese Amazon. And the data we use is from 1 month, and we adopt one top selling product. We mostly consider the data from the tables of the orders, the users, and also the product. And to evaluate our model, we use the customer surplus, social welfare to evaluate the benefits of the outcome of our model. And also we evaluate the fairness of our model by the Gini index. So we did some preliminary analysis to justify the assumptions of our model. And now, so to show the benefits of our pricing policy, we compare our pricing policies with various baselines, such as the single price constraint, the mean price constraint, and the unconstrained model. We show that our model provides a more equitable and efficient pricing policy. We also show that a stricter fairness regulation leads to higher customer surplus, social welfare, and lower Gini index under some regular conditions. And our model also, an analysis result also guide decision makers in selecting an appropriate fairness degree delta to balance the revenue and social welfare considerations. And we also compare our result with other baseline models, and we find that our model excels in enhancing the social welfare and ensuring equitable price distributions. And as a side product, we also analyze on a price discretization, and we find that when we increase the number of prices under fairness constraint, it will lead to higher revenue. We also show on the right-hand side graph that the gap of the revenue converges at a rate faster than linear, which is also proved in the theorem 2. So we can conclude that it is preferable to choose a moderate size of price set, as aggressive discretization may not yield significant rewards. So to conclude, in this work, we propose a stochastic formulation to model the personalized pricing problem for different groups under fairness constraint. We also reformulate this revenue maximization problem with statistical parity constraint into a linear programming under the sample average approximation. Theoretically, we established an order of 1/L gap for the optimal revenue between the continuous and discrete price set of SL. And in our numerical experiment, we demonstrated the benefits of fairness constraint over several baselines. And we provided a managerial insight on this determining appropriate fairness degree and selecting an appropriate size of discrete price. So all the results can be extended to the Earth mover distance and other demand models. And there are also interesting future directions to think about. One is we can consider other popular distance metrics such as H divergence or KL divergence. And also it will be also interesting to find the lower bound of the optimal gap in a theoretical result. So that's all. Thank you.
Thank you. For the last talk, we will have a video, and we will be learning about the paper, We Are Adults and Deserve Control of Our Phones, examining the risks and opportunities of a right to repair for mobile apps.
Hello. Thanks for making it to our talk today. I'd like to present our latest work on a right to repair for mobile apps today, which is motivated by the fact that many countries, including US states and the European Union, are currently debating introducing a right to repair for hardware, like tractors, but don't really consider software, which obviously is getting increasingly important, so we believe this is a timely subject to study. Let's get started. What you see here could be the PhD students at the University of Oxford in their final year. It could also be a metaphor of how human civilization a couple of years back really used to be about finding tools that would enable our survival, and those would get better over time through a process of tinkering and fixing and keeping improving to fit our needs. Fast forward to the 21st century, we have somewhat lost that ability to fix the tools that we use in our daily lives. For example, those of you who have a John Deere tractor will know about the struggle of fixing the latest iterations of them, since John Deere has been locking them down a lot and has been making independent repair very cumbersome. And so a range of states in the US have already introduced legislation against that. Now, going from hardware like tractors to software in the mobile app ecosystem, which is really so widespread these days, there's a really broad range of harms these days, like disinformation, lack of privacy, or accessibility issues. And for many of them, we still don't have a good solution yet. Surely academia will make a contribution to those, but maybe we should have a means to give those most severely affected by these harms an ability to find solutions themselves. And so, taking a bit of a philosophical view, since you probably know that dignity, autonomy, and development of personality are fundamental legal principles, then might an ability to repair apps, to overcome those harms that are embedded into apps and might significantly affect me, might then such a right to repair apps help protect those principles. Based upon all those observations, we devised 2 research questions to study in our piece of research. First of all, we looked into the needs for app repair and tried to identify common, pressing, or important needs users have that require modification of their apps. Secondly, we looked into the barriers of doing so, taking a multifaceted approach to that and studying practical, ethical, technical, societal, and legal challenges in doing so. The ultimate aim of the study is not to argue that this technology must be widely adopted, but rather, prior to such a wide adoption, to understand what the risks entailed are, as well as the potential benefits. In the future, legislators may then decide to foresee explicit support for app repair functionality in mobile app ecosystems, since the practical implementation of them still remains difficult due to limitations imposed by Google and Apple in their respective app ecosystems. To study these highly interdisciplinary research questions, we opted for a mix of various methods. You could also say we just threw everything that we had at these research questions so as to really get fine-grained, nuanced, informed results. This involved a survey with 100 participants, asking them what they'd like to change, why, and how they feel about app repair in general. This included a prototype, a technical prototype, and a couple of case studies to understand the feasibility of the approach, as well as practical and legal challenges. And lastly, we conducted 8 expert interviews to be able to conduct a detailed and nuanced ethical and legal analysis of app repair. The main part of our survey was asking 100 participants about what they'd like to change about the apps that they regularly use. The participants, across all of them, came up with 700 suggestions as to what to change. We excluded 150 of these suggestions from our thematic analysis because these suggestions were either not actionable or relevant for app repair. Among the remaining suggestions, we identified 3 categories of actionable and relevant app changes. Firstly, users expressed the wish to make apps business models more user-friendly and respectful. For example, reducing highly engaging elements in apps, or being annoyed by the amount of ads that they see in the YouTube app. That was a very common concern. Secondly, there was a wish for more attractive, user-friendly, accessible user interfaces. For example, one participant expressed the wish to make an app more suitable for educational settings and made suggestions as to how to accomplish that. Lastly, a common concern were privacy and security issues in apps, both in relation to companies as well as in relation to other users. We now turn to our technical prototype. This is slightly different to what we present in the paper because we've evolved it a bit, but the idea is the same. In the first step, the user would select the app that they want to make a modification to, for example, the Twitter app in this example. In the second step then, the user selects from a range of pre-installed modifications to the app. Those are developed by so-called patch developers, who are similar to browser extension developers on the web, experts in programming who sort of have crafted these patches. And in the last step, these modifications then get applied to the app and the user reinstalls the modified app on their phone. As a result of the process we saw just now, end users with the Greasejoy tool can remove distracting elements from the Twitter app, like the stories bar at the top, or annoying notifications that cannot currently be disabled in the Twitter application. We also conducted 4 other prototypes. If you're interested in those, please refer to our paper. And based upon those prototypes, we made a couple of observations. First of all, we found that making changes to the user interface of existing Android apps is pretty straightforward if one has previously worked with Android app development, because the approach is the same. Secondly, we find that making changes to the underlying code of apps requires sophisticated programming skills. These might be available in computer science academia, but outside of technical disciplines, it is probably very hard to say run a study with participants based upon app repair technology to, say, study the impacts of certain design patterns in apps on individuals. So this is clearly some space that should be improved in future work. Lastly, we worked with a couple of legal experts to understand the legal implications of such a tool, and we do see some concerns outside of research settings when it comes to the use of app repair functionality. However, we see that once a legislator would establish clear obligations on providers of software to foresee app repair functionality, then these should be mitigated. So maybe this is just some legal vacuum that still needs to be addressed. Based upon all the evidence we gathered in our paper and an additional 8 expert interviews, we then do a very in-depth ethical analysis of app repair, talking about the benefits and opportunities, as well as the risks and challenges in such a design. The reviewers really like this part of the paper, but it would be too much for this talk to go into that now. Yet, if you're interested, I encourage you to just have a look at our paper. This is it for me from now. If you're interested to hear more, feel free to reach out or to ask questions. Thanks so much.
Okay, this finalizes all the papers that we were going to listen from. And now I'll ask the authors to come to the front and we'll open the floor for questions. And for questions, you can use that mic over there. And I'm going to give you all this microphone that you can pass along. And I'll start with a question for all of you. There's the title of the session has diversity in it, and I think that the very heterogeneous set of papers shows us how heterogeneous the concept of diversity is, both in terms of diversity of what, as well as what concept of diversity we're using, what do we consider to be maximally diverse. And so I was wondering if very briefly you could each talk about what is the definition of diversity that your paper is relying on.
So in my paper, so this is the diversity between counterfactual explanations, and the goal is to have different informations from each counterfactual. And that's why there is 3 types of diversity in criteria, in feature space, and in action. But the main goal is to have different explanation and have different information from each explanation for give all the choice for the user and let him choose which one is the best for him.
Yeah, I guess for our paper, I think that maybe it doesn't fit into this very traditional idea of diversity so much as it is, that saliency methods experience algorithmic diversity, and so do the use cases that people employ them in. And so that given we have diversity across both of those aspects, to sort of categorize that space so we can best understand it.
So for our work, one thing I think is the diversity of the application. So it can be applied to, besides business world, it can also be applied to other different fields. So that's, I think it's the application diversity mostly. And in terms of methodology, and also the fairness constraint, I think we also consider the diversity of the policy, that we don't restrict on a specific policy, but we consider the diversity or distribution of a policy. Yeah, thank you.
Thank you all. Any questions from the audience?
I have a quick question for the price discrimination paper. So you motivated the talk by talking about pink tax, right? So I guess my question is for like maybe a special case of your setup where, let's say, like different users or different consumers have like non-overlapping preferences. So like they have 0 value for the products that the other group likes, and they only have non-zero value for like a particular group, and there's like no overlap at all. So in that scenario, like, is there like a specific thing that your model converges to, or like have you thought about that?
Okay, thank you. That's a very great question. So our model actually imposes assumption that when we consider on the sensitive attributes, the normal features has to be the distribution of the normal feature of the different groups have to be similar. So this case will be ruled out. Yeah, but that will be also an interesting question to think about. Yeah, we can we will extend, maybe think about this extension or extreme case later. Yeah, thank you.
Thank you for the excellent presentations. I have a question for Angie on saliency cards. So I was wondering if you can comment on the relationship between saliency cards and data sheets, like how, because a lot of the saliency metrics or any evaluation explanation methods will also depend on the data sets that were used to evaluate those metrics. So like, what are your thoughts on how these two can be like read together, these two kinds of cards?
Yeah, that's a great question. I think that, data sheets or for data sets or model cards or saliency cards are all, in the same vein of transparency documentation. And I think they all play a really important role and are, to some extent, like you're mentioning, overlapping, right? We train our models on data sets that have their own documentation, and those were collected for tasks and so on and so forth. So I think that something that came up when we were talking to users a lot is that we have evaluated saliency methods through these different saliency evaluation tests, like sanity checks and a multitude of other papers that we characterize. But a lot of times people were really interested in how that test applied to their task. So while a test may have been done in an image setting on ImageNet, on a ResNet, they would wonder how that same test would work if you ran the saliency method on their medical data with their models in their setting. So I think that that's a really open space and rich area to think about is, do our saliency methods pass these tests just in this one domain, or do they fully pass them in all the domains? And could we even test them more specifically for specific tasks and data settings?
I have a question for Adulam. You talked about the 3 types of diversity that you focus on. And one of the directions of future work that you pointed out is looking at which one was more relevant to a user. And so I was wondering if you could talk a little bit more about this, and in particular, how the different types may be relevant for different goals of explanation. Sometimes we want counterfactual explanations for recourse. Sometimes we wanted to assess some properties of the model. And so how do you see this typology relating to the goal of the explanation?
So that depends on the context that we are studying, the goal of the user. There is really a lot of factors. So with diversity, I think we can cover all kind of people, kind of cases. And in this way, even if we don't know the needs of the user, we can give him the explanation and let him choose which one is adapted to him. So that's why I think it's very interesting to give several explanations, because there is a lot of factors that we don't know. Like if the counterfactual explanation is for learning something or for something actionable. So giving several explanations can let him choose which he wants.
Any final questions? Yes.
Hi. Thank you guys all for the talk. I had a question for Zixing about when you're looking at the data, at the JD.com data, is the only notion of fairness just on that, male female, or is there any other notions of diversity that's kind of available for you to look at there? Thanks.
Yeah, thank you for the question. So in terms of the data set, there are also other sensitive features as well. If you want to treat the age group as sensitive feature, you can also use that. But that data set, because that's also from e-commerce platform, they cannot release too much like the customer's features as an open source. So they that's the only sensitive or non-sensitive attributes that we can acquire. But since from the preliminary analysis, we detect that if we consider the sensitive group as as gender, let's say the female and male and female, then we can observe an initial bias of the existing pricing policy, which means the female group and the male group have a different distribution of the pricing policy from their initial data set.
And is that on the SKU item ID level, or is it more in general that pricing difference, if that makes sense?
Yeah. So that's on because we only select one SKU, so it's actually on a customer order level.
Got it.
Yeah.
Thanks.
Yeah. Thank you.
Any last questions? Okay, so with this, I want to thank the authors again. And we now have a keynote, a break followed by a keynote, and then the town hall that I encourage you all to attend and participate in. Thank you all very much.